Okay, hello everyone. In a new video, so we have reached part 3 of chapter 5, which is the chapter of electric power and energy in the second unit of electricity. In this one, we are going to solve some exercises. Then we have reached section number 17, exercise number 9. The aim of this exercise is to compare the sum of the electric power consumed by a grouping of resistors with that consumed by the equivalent resistor of this grouping. Consider the circuit of the below figure. Then they mention the circuit, now we can use it. They are telling me that R1 is 60 ohms. R2 is equal to 30 ohms. And R3 is equal to 20 ohms. The value of the current I1 is equal to 1 amperes. Then the trick in solving such type of exercises is to write the applied and the reversed voltage current respectively on the electric circuit itself. Then here we have that the value of I1 is equal to 1 amperes. Now part 1, power consumed by the grouping, 1.1. Calculate the voltage UAM across the terminals of R1. So mainly we have two methods to calculate, or three methods to calculate the voltage UAM. Here, because we know the resistance R1 and we know the value of I1, so we can apply Ohm's law to R1 in order to calculate the voltage UAM, which is the same for R1 and R2. Then let's say apply Ohm's law to R1. Ohm's law is given by U is equal to R multiplied by I. No need to construct a triangle because we are interested in determining the value of U, which is across R1 given by UAM, R1 traversed by the current I1, which is equal to 60 multiplied by 1, which is equal to 60. Since everything is expressed in the SI, so the value of UAM will be in the SI, which is volts. Then UAM is equal to 60 volts. And I repeat, the trick in solving such type of exercises is to write the applied, reversed voltage current respectively on the electric circuit. Then here we have 60 volts, which is the voltage UAM. Now in 1.2 we are interested in determining, show that the current carried by R2 is I2 is equal to 2 amperes. Then mainly we have three methods to determine the value of I2, but here since we know the voltage UAM, which is 60, and we know the value of R2, then we can apply Ohm's law to determine the value of I2. Then in this case you are applying Ohm's law to R2. And Ohm's law is given by U is equal to R multiplied by I. Notice that we are interested in determining the value of I. Then constructing the triangle of this formula, I'm putting our hand over I. And then the value of I is given by U divided by R. Notice that we are calculating I2 that have an applied voltage UAM across the resistor R2. Then 60 divided by 30. So this is equal to 2. Since everything is expressed in that SI, so the value of I2 will be in that SI, which is amperes. Now in 1.3, deduce the current I carried by R3, and by deduce it means that we notice the previous part. In the previous part we have determined I2 and we know the value of I. Then the value of I, which is across the terminals of R3, can be determined by applying the law of addition of currents, because notice that at the point M, currents I2 and I1 at the point A they split into I1 and I2, and the point M they join back to give me the main current I. Then let's say apply law of addition of currents. So always on the left in physics always we need to mention the law, this is the first thing. And always on the left we write the main current, which is I, and on the other side of this equation we write the current traversing different branches, and they are given by I1 plus I2, because notice that I1 and I2 join back at the point M to give me the main current I. And we are interested in determining the value of I. So what's the type of this equation? Linear equation and one unknown, because now if we replace the value of I1 and I2, this is equal to 3. I1 and I2 are expressed in amperes, so the value of I is in amperes. Then I is equal to 3 amperes. And now we are in 1.4, calculate the electric power consumed by each of the 3 resistors. Here let me say that this is I is equal to 3 amperes. So we are interested in determining the electric power which is given by P is equal to U times I across each of the 3 resistors. So let me say electric power across R1. So the electric power across R1 is given by the main form, which is given by P is equal to U multiplied by I. So this is P1. No need to construct a formula because this is the quantity that we want to calculate, having an applied voltage UAM traversed by the current I1. So the value of UAM is given by 60 and the value of the traverse current is 1. So this is equal to 60. Since everything is expressed in SI, so the value of P1 will be SI, which is watts. So P1 is equal to 60 watts. Now we need to determine the electric power across R2 as well. Then the electric power is given by P2, which is equal to UAM multiplied by I2, which is equal to 60 multiplied by 2, which is equal to 120 watts. And now the electric power across R3. So now in this case, we need to calculate the power which is equal to U multiplied by I across R3. But notice that we don't know the voltage UMB across R3. But the important thing is that we are calculating the power across a resistor, and we know that a power across a resistor has 3 different forms, and they are given by P is equal to U multiplied by I, P is equal to U square divided by R, or even P is equal to Ri square. Okay, now in this case, which one of these we need to use, the general form or U square over R or Ri square, and this depends on the given. Here in this case we have the resistance which is given by R3 is equal to 20 ohms, and we have the value of the current. Then we will use this form instead of the general form and the other form. Okay, but notice that, recall that before we use this we need to prove it. So we are interested in proving that P is equal to Ri square. So in this case, if we compare this form which is given by P is equal to Ri square, which means that we need, because R appears, it means that we need to apply Ohm's law and to get rid of U. So let me say U is equal to R multiplied by I, and this is given by Ohm's law. So now replacing this expression and this one, we get that this is equal to R multiplied by I, which is equal to R II given by Ri square. So in this case we have that P is equal to Ri square, and now we are ready to calculate the electric power P3 across the resistor I3 traversed by the current I. The value of R3 is given by 20. The value of I is given by 3. So now plugging this expression on the calculator, then we have that this is given by 180. Since everything is expressed in that side, so the value of P3 will be in that side, which is watts. So P3 is equal to 180 watts. Now in 1.5, deduce the total electric power P total consumed by the three resistors. So, and by deduce it means that we need to use the previous part. In 1.4 we have determined P1, P2 and P3. So how come P total is related to these? P total means the sum, so simply P total is equal to P1 plus P2 plus P3. Now the value of P1 is given by 60, the value of P2 is given by 120, and the value of P3 is given by 180. Plugging these values on the calculator, we can check that the value of P total is given by 360. Since all of these are expressed in watts, so the value of P total will be in watts. So P is total is equal to 360 watts. Now in part 2, they are telling me power consumed by the equivalent resistor. 2.1, so this is not a question, just a title. 2.1, calculate the resistance R prime of the resistor equivalent to R1 and R2. So first, we need to check the grouping of R1 and R2. We can check that they are in parallel. So in this case, the equivalent resistance, which is denoted by R prime, is given by 1 over R prime, which is equal to 1 over R1 plus 1 over R2. Now the value of R1 is given by 60. The value of R2 is given by 30. And here we need to take into consideration that we are adding two fractions. We need to take the common denominator, then simplify this fraction, then it's given by 1 over 20. So now in this case we have determined the value of 1 over R prime. So simply R prime, if we cross multiply, it's given by 20 ohms. Why ohms? Because R1 and R2 are expressed in ohms, okay? And recall that whenever we determine an equivalent resistance, we redraw a new electric circuit in which the new equivalent resistance is represented. So R prime replaces R1 and R2. So this is R3, this is R prime. Here we have that R prime is equal to 20 ohms. Okay, so and here the value of the electric current I. So notice that here in this case, these two branches 1 and 2 disappear and we are left with the main branch which is reversed by the current I, which is equal to 3 amperes. Okay. Now in 2.2, so this is the point A, this is the point M, and this is the point B. In 2.2, they are telling me show that the resistance equivalent to R prime and R3 is RE is equal to 40 ohms. So notice that R prime and R3 are in series. In this case, the equivalent resistance, which is denoted by RE, is given by R prime plus R3, which is equal to 20 plus 20, because R prime is given by 20 and R3 is given by 20, which is equal to 40. Since both of these are expressed in ohms, so the value of RE will be in ohms. So RE is equal to 40 ohms. And now we represent RE instead of all of these groupings. So the point M eventually will disappear, and we are left with the point A, with the point B, and the value of I is equal to 3 amperes, and we have that RE is equal to 40 amperes. Now in 2.3, they are telling me calculate the electric power PE consumed by RE. So here we are interested in determining the electric power consumed by RE, and we have three different forms of power. P is equal to 2 times I, P is equal to E square over R, and P is equal to RI square. Which one we should use? And this depends on the given. Since we have the value of I and we have the value of RE, then we will use this one. And in this case, no need to prove it, because this we have already proved in part 1.4. So electric power or without mentioning electric power across RE, let me directly say that PE is equal to RE multiplied by I square. So the value of RE is given by 40 multiplied by 3 to the power 2. Plugging this fraction on the calculator, then the value of PE is given by 360, since everything previously is expressed in the SI. So the value of PE will be in the SI, which is watts. Now finally, part 3, the comparison of electric powers. They are telling me to compare P total with PE. Now P total that we have calculated is given by 360 watts, and PE is given by 360 watts, and by compare we need to mention whether P total is greater than PE, less than or equal, making sure that both have the same unit. So in this case it's obvious that they are equal, which means that the electric power of a grouping of resistors can be determined using two methods. The first method is given that we calculate the electric power of each resistor, then we add them up. The second method is that we calculate the equivalent resistance, then we calculate the electric power of this grouping using the electric power across the equivalent resistance. Now let me move to the second exercise, which is exercise number 10. Now they are telling me, given the following documents where each one represents the characteristic current voltage curve of three electric components D1, D2, D3 respectively. So this characteristic current voltage curve is for D1, this is for D2, and this is for D3. Indicate which of them is an ohmic conductor. So an ohmic conductor, the shape of the curve is a straight line passing through the origin. So notice that this is a straight line, but its prolongation is not passing through the origin. This is a straight line passing through the origin, and this is not a straight line. So document 1 is an ohmic conductor. Now since the shape of the characteristic current voltage curve of document 2 is a straight line passing through the origin, then document 2 represents an ohmic conductor. So this is it for exercise number 10. Now for the aim of this video, we will skip exercise number 11. Now as for exercise number 12, they are telling me the below documents represent the characteristic current voltage curve of three ohmic components, D1, D2, and D3. Find graphically the resistance of each. Let's start by document 1. So the resistance can be determined by using the slope method. So first, the slope method consists of several steps. The step number 1 is to write the definition. So the resistance of the resistor is equal to the slope of the characteristic current voltage curve Now the next step is to choose 2 points. So the first point I will choose here to be the point A, and this is the point B. Now let's write the coordinates of these points. So these are the only 2 points that are clear in this graph. So this is given by 0.01 amperes, and as the voltage is given by 2 volts, whereas for the point B it is given by 0.02 amperes, and the voltage is given by 4 volts. Notice that these are in the SI, so now we are ready to calculate the resistance. Say for example this is R1, R2 and R3, which is equal to UA minus UB divided by IA minus IB. So the important thing that if we have started with A, then in the denominator we must start also with A. So the voltage UA is given by 2 minus 4 over the current of the point A, which is 0.01 minus 0.02. Now plugging this expression on the calculator, we have 2 divided by 0.01, which is equal to 200. Since we make sure that everything is expressed in the SI, so the value of R1 will be in the SI, which is ohms. So R1 is equal to 200 ohms. Now as for document 2, so we always start by writing the definition, which is given by the resistance of the resistor is equal to the slope of the characteristic current voltage curve Now let's choose 2 points. So suppose that this is the point C and this is the point D. So what are the coordinates of the point C? C is given by 200. Notice that here the unit is given by milliamps, and the voltage is given by 0.04 kilovolts. As for the point D is given by 400 milliamps, and the voltage is given by 0.08 kilovolts. Now the next step is to convert these units to the SI. So for the point C, notice that in order to convert from milliamps to amps, we divide by 1000. So this is given by 0.2 amperes, and in order to convert from kilovolts into volts, we multiply by 1000. So this is given by 40 volts. Similarly for the point D, it's given by 0.4 amperes and 80 volts. Now we are ready to calculate the resistance R2, which is given by UC minus UD divided by IC minus ID. So the value of the point UC is given by 40 minus 80 divided by 0.2 minus 0.4. Now plugging this expression on the calculator, we have 40 or minus 40 divided by minus 0.2. Then it's given by also 200 ohms. Then R2 is equal to 200 ohms. So notice that although the values of these points and the units across the axes of this curve are different, but they have the same resistance. And now as for document 3, so we also start by writing the definition, which is given by the resistance of the resistor is equal to the slope of the characteristic current voltage curve So now let's choose 2 points. So suppose this is the point E and this is the point F. The coordinates of these points are given by E. We always start by the current, which is given by 250 milliamps. And its voltage is given by 3000 millivolts. As for the point F, is given by 500 milliamps. And the voltage is given by 6000 millivolts. Now the next step is to make sure that these values are in the SI. So notice that they are not in the SI. In order to convert from milliamps to amps, we divide by 1000. And in order to convert from millivolts to volts, we divide by 1000. Then the value of E is given by 0.25 amperes and 3 volts. And the value of F is given by 0.5 amperes and 6 volts. So now we are ready to calculate the resistance, which is denoted by R3, which is equal to UE minus UF. So IE minus IF. So as you can notice that always we start by the same point and end with the same point, independent whether we start by E or by F. So 3 minus 6 divided by 0.25 minus 0.5. Now plugging this fraction on the calculator, we have that the value of the resistance is given by 12, since everything previously is expressed in the SI, so the value of R3 will be in the SI, which is ohms. So this is it for exercise number 12. Now for the same reason, we will skip exercise number 13. And we'll move to the final exercise of this video, which is exercise number 14, section 22. The aim of this exercise is to show that the resistance of a voltmeter is very large. So this aim is important. For this, we consider the series circuit that is represented in document 1, which is formed of. So they mentioned document 1, now we can use it. Notice that they didn't mention anything about document 2, we are not allowed to use it. They are telling me a generator G maintaining across its terminal a constant voltage UPN, which is 12 volt. Then the trick in solving such type of exercises to write the applied voltage on the electric circuit itself. So an ammeter A of negligible resistance, two resistors R1 and R2 of resistances R1 is equal to 10 ohms and R2 is equal to 20 ohms. Respectively, and the switch key. Number 1. The voltage UPP across A is 0, which is the voltage across an ammeter, since it is of negligible resistance. Since it is of negligible Now in number 2, they are telling me the voltage UDN across K is 0. Notice that K is a closed switch acting as a connecting wire. Here let me say that UPB is equal to 0. Since it acts, or because it's the same, since it acts so we have that UDN is equal to 0. So notice that because they asked me about voltages across different branches, now we expect that they ask me about which law, the law of additional voltages. And indeed, in part 3, they are telling me deduce the voltage UPN is equal to UBD, and by deduce it means that we need to use the previous part. So, which is, in the previous parts we have discussed voltages across different branches. Then apply law of addition of voltages. So on the left hand side of this equation we write the voltage UPN, and on the other side of this equation we write voltages across different components starting from P and ending with N, making sure that also both UPN and UBD must be kept as a variable in order for them to appear in the equation. So from P to A, now from A we can go directly, from P to B. Now from B we can go directly to D or across the point C. Since we want UBD to appear in the equation, then we will go to D plus UDN going back to N, making sure that UBD and UBN must be kept as a variable. So 0 plus UBD plus 0, then in this case UPN is equal to UBD. No need to justify why UPB and UDN are 0 because this is done previously. Now in part 4, they are telling me to calculate the equivalent resistance R equivalent to R1 and R2. Notice that they are in series. So R1 and R2 are in series. Then their equivalent resistance, which is denoted by R equivalent, is equal to R1 plus R2, which is equal to 10 plus 20, which is equal to 30 ohms, because R1 and R2 are expressed in the SI. Then R equivalent is equal to 30 ohms. And recall that whenever we calculate an equivalent resistance, it's convenient to represent this equivalent resistance in the new electric circuit. So this is the ammeter. This is the point B. The point C eventually will disappear. This is the closest switch K. This is the point N. This is the point P. This is G, which is given by 12 volts. And here we have an important result that UPN is equal to UBD. Now in part 5, they are telling me calculate the current flowing in the circuit. So notice that this is a closed circuit, which means that it will be traversed by a current I, and which is measured by the ammeter, and the direction of this electric current is always from the positive pole to the negative pole. Now, because here we have a resistance R equivalent, and the resistance and its resistance is given by 30 ohms, and we know because UPN is equal to UBD, so if this is 12 volt, this is 12 volt also, because simply UPN is equal to UBD, proved in part 3. Then applying the Ohm's law to I, applying Ohm's law to R equivalent, we can determine the value of I. In this case, apply Ohm's law to R equivalent, which is given by U is equal to R multiplied by I. Constructing the triangle of this formula, U at the top, R and I at the bottom, we are interested in determining the value of I, which is equal to UBD divided by R equivalent. So this is equal to 12 divided by 30. Plugging this on the calculator, then the value of I is given by 0.4. Since U and R are expressed in the SI, so the value of I will mean the SI, which is amperes. Then I is equal to 0.4 amperes. And the trick in solving such type of exercises is to label the value of the electric current on the electric circuit itself. Here we have several electric circuits, so we must also label the value of the electric current here to be I is equal to 0.4 amperes. So I have erased this circuit knowing that I will not use it in the coming parts. Now in part 6 they are telling me show that the voltage UCD is equal to 8 volts. Notice that the voltage UCD at least can be determined by 3 different methods. Here, because we know the value of the current traversing R2 and we know that the value of R2 is given by 20, so simply UCD can be determined by applying Ohm's law to R2. Knowing that the law of addition of voltages cannot be applied because we have two unknowns, UBC and UCD, so the number of unknown is greater than the number of equations. Then apply law of addition of, apply Ohm's law to R2. So UCD is equal to I multiplied by R2, which is equal to, R2 multiplied by I. So use the same notation, okay? It's the same. The value of R2 is given by 20 multiplied by 0.4, so this is equal to 8. Since both R2 and I are expressed in the SI, so the value of U will be in the SI, which is volts. So UCD is equal to 8 volts. And now, let's label this voltage here. Now in part 7 they are telling me we connect between C and D a voltmeter V that can be considered as a resistor of resistance R as shown in document 2. Then they mention document 2, now we can use it. And let me repeat that we connect between C and D a voltmeter that can be considered as a resistor of resistance R. So simply we can apply Ohm's law to this voltmeter, which is of resistance R. The current flowing in the voltmeter, so this is the current I prime, which is equal to 0.01 milliamperes. Okay, and recall that in order to convert from milliamps to amps, we divide by 1000. So let me write here that the value of I prime is equal to 0.01 milliamps, which is 0.01 divided by 1000, which is equal to 1 times 10 to the power 5. So this is equal to 0.00001 amperes, or simply in the scientific notation, 1 times 10 to the power minus 5 amperes. Now in 7.1 they are telling me, knowing that the voltage UCD remains 8 volt, so this is 8 volt, calculate the resistance R of the voltmeter, and for sure always the resistance can be determined using Ohm's law. Then apply Ohm's law to the voltmeter, which is given by V, and Ohm's law is given by U is equal to R multiplied by I, knowing that we are interested in determining I. So constructing the triangle of this formula, the value of R is given by U, which is UCD, divided by the current traversing it, which is I prime. So 8 divided by the value of I, which is 1 times 10 to the power minus 5. Plugging this expression as it is on the calculator, then it's given by 8 times 10 to the power 5. Or simply because this is in the denominator, when it goes up to the numerator, this sign will flip from minus to plus. If it's plus, it will be minus. Then it's given by 8 times 10 to the power 5. Since everything is expressed in the SIU and I prime, then the value of R will be in the SI, which is ohms. Then R is equal to 8 times 10 to the power 5 ohms. Now in 7.2 they are telling me deduce that the calculated value of R satisfies the aim of the exercise. So now let's refer back to the aim of this exercise. The aim of this exercise is to show evidence that the resistance of a voltmeter is very large. Now we need to refer to the aim and to the calculated value. Now notice that previously all the calculated values of R range from, say for example, 10 ohms to 1000 ohms at most, or let's say 10,000 ohms. But now this value is given by R is equal to 8 and 5 zeros, 1, 2, 3, 4, 5, which is given by 800,000 ohms. So whenever we face such a number, which means that this resistance is very high, because previously all the values that we have faced is given by or range between from 10 to 10,000. This is similar to say that a current is of value, say for example 10,000 amperes. So this is extremely large, because all the currents that we have faced previously ranges from 0.001 amperes into at most 10 amperes. Okay, so always we need to keep an eye on the order of magnitude. So in this case, let me say in 7.2, since R, let me write it as a whole number, which is given by 800,000 ohms, is very large, then the calculated value of R satisfies the aim of this exercise. So that's it for me in this video, guys. In part 4 we will solve more exercises on this chapter.